As of May 25th, 2026, NASA's Solar Orbiter spacecraft, currently positioned to image the side of the Sun that no Earth-based instrument can see, has confirmed that large, magnetically complex sunspot regions are rotating toward the Earth-facing disk, and NOAA's Space Weather Prediction Center has already issued an official 27-day forecast, acknowledging that X-class flares, rated R3 strong, are a credible near-term possibility from regions both visible and approaching. And what the far-side magnetic imagery is revealing about what is coming next is not the kind of data that allows you to look away. If you rely on this channel for science that is grounded in verified data and explained with honesty, subscribing ensures that none of this reaches you late. This work depends on the audience that values it. Every figure in this script was drawn from official scientific and governmental sources: NOAA's Space Weather Prediction Center, NASA's Solar Dynamics Observatory, the ESA Solar Orbiter Mission, USGS Geoelectrical Hazard Studies, peer-reviewed research published in journals including PLOS-1 and Space Weather, and the documented record of congressional testimony before FERT. But official sources are not infallible, and neither is the human process of reading them. Before any decision is made, whether personal, professional, or otherwise, verify independently through the official channels. The sources are listed. The data is public. The responsibility to check belongs to all of us, but that is not even the complete picture. Because what is unfolding right now is not simply a story about a sunspot. It is not simply a story about a flare or a coronal mass ejection or even a geomagnetic storm. What is unfolding right now is the convergence of three separate facts that, taken individually, each deserve serious attention, but taken together form a sequence that the historical record has already shown once can collapse an entire regional power grid in 90 seconds. The sunspot regions now being tracked by Solar Orbiter on the Sun's far side are rotating toward Earth. The American power grid, specifically the high-voltage transformer network that carries electricity to an estimated 130 to 140 million people across the northern and eastern United States, remains, by the testimony of its own regulatory engineers, and confirmed in peer-reviewed literature as recently as March 2026, structurally vulnerable to the precise type of geomagnetically induced current that a G4-class storm produces. In solar cycle 25, the current 11-year cycle of solar activity that peaked near solar maximum in late 2024 and early 2025 has already demonstrated its capacity for extreme events, including the G5 storm of May 2024 that registered a DST index of negative 412 nanoteslas, and the G4 storm of January 19, 2026, when NOAA confirmed that severe geomagnetic storm levels were first reached at 1938 UTC upon CME shock arrival. The question is not whether the Sun can do this again. The question is not whether the American grid is vulnerable to it. Both of those questions have been answered. The question, the one the instruments cannot yet resolve, is when. To understand what Solar Orbiter is seeing right now, and why NOAA's most recent 27-day space weather forecast specifically names it as a factor that could change everything about the coming weeks, you need to understand what the spacecraft is doing and why its position in the inner solar system right now is not routine. Solar Orbiter is a joint ESA and NASA mission. It does not orbit Earth. It orbits the Sun itself on an elliptical path that periodically takes it to vantage points far outside the ecliptic plane and, critically, around the Sun's limb, meaning it can observe active regions on the far side of the Sun that are completely invisible from Earth. As of NOAA's official space weather advisory issued on May 18, 2026, far-side imagery from Solar Orbiter was already prompting forecasters to state explicitly that while near-Earth solar activity looked calm, the forecast could change for May 20th and beyond. That language, spare, measured, official, is itself the warning. When NOAA's forecasters use the phrase "the forecast could change," what they mean in the context of solar physics is that something they cannot yet fully characterize is already moving in their direction. What Solar Orbiter's magnetic imagery has confirmed as of the final days of May 2026 is that large sunspot regions lurking on the far side of the Sun are approaching the eastern horizon of the solar disk as seen from Earth. This is not speculation. It is the combined output of Solar Orbiter's direct far-side imagery, helioseismic echo mapping of subsurface magnetic flux, and confirmation from NASA's Perseverance rover on Mars, which has independently imaged far-side solar activity from its position on the Martian surface. 3 independent detection systems, operated by 2 space agencies, pointing at the same hidden region of the Sun and arriving at the same conclusion: something significant is rotating into view. And the last time NOAA saw comparable far-side magnetic signatures rotating toward Earth, the result was the most intense geomagnetic storm in more than 2 decades. Sunspot region AR4436 has already demonstrated what the current cycle's active regions are capable of. On May 22, 2026, AR-4436 produced an M2 4 flare that peaked at 10:29 UTC and launched a coronal mass ejection captured by the LASCO C2 coronagraph aboard the SOHO spacecraft. That M2 4 event occurred as AR-4436 was already rotating beyond the northwest limb of the Sun, meaning it fired that flare while partially out of Earth's direct line of sight, with the coronal mass ejection angled away from us. An M2 4 is a mid-range flare. It is not what the solar orbiter magnetic imagery is warning about. What the imagery is warning about is what comes after. The regions still rotating into view, still accumulating magnetic complexity, still building the kind of intertwined magnetic structure that, as research published in January 2026 in peer-reviewed literature confirmed, preceded the strongest solar flare in over 20 years. The researchers who tracked sunspot region AR-3664 across 3 consecutive solar rotations for the first time ever watched the magnetic field grow more complex with each pass. They documented the formation of an intertwined magnetic structure right before the Sun released an X-class event that sent a G5 storm into Earth's magnetosphere. The system does not erupt randomly, it accumulates. The system is not inactive, it is accumulating. Here is where this account becomes genuinely significant. The G4 storm that NOAA confirmed reached Earth on January 19, 2026 at 2:38 in the afternoon Eastern Standard Time was not a fringe event in the statistical sense. It was a severe storm on the official 5-level NOAA scale, one step below the extreme G5 classification. A G4 storm is defined by a KP index of 8, widespread voltage control problems in power systems at high latitudes, possible tripping of grid protection systems, and long-duration disturbances in satellite navigation, high-frequency radio communications, and pipeline corrosion monitoring. A G4 storm is the kind of event that engineers at grid operations centers prepare contingency protocols for. A G4 storm is, in the language of the Newsweek report on that January 2026 event, the kind of space weather that puts power grids in at least 11 states at risk simultaneously and makes geomagnetically induced currents in visible rivers of quasi-DC electricity flowing through the Earth's crust and finding their path. Of least resistance through the neutral-to-ground connections of high-voltage transformers, the specific technical threat that every power utility at high geomagnetic latitude is supposed to be monitoring in real time. The reason the January 2026 storm did not collapse the northeastern grid is the same reason the May 2024 G5 storm did not adequate structural protection, but the particular geometry of the magnetic field when the CME arrived, the orientation of the interplanetary magnetic field's southward component, and the duration of the most intense pressure. The grid survived because the conditions were not, in the precise technical sense, perfectly aligned. The instruments were measuring, the systems were stressed, but the alignment was not complete. That alignment, when it arrives, is what the record already shows can happen in 90 seconds. The record is not hypothetical. On March 13, 1989, a coronal mass ejection from active region NOAA 5395, which had produced an X-15 flare, struck Earth's magnetic field. The geomagnetic storm reached a KP index of 9, the maximum possible. The DST index plunged to negative 589 nanoteslas. At 2:44 in the morning on March 13th, in the province of Quebec, the Earth's magnetic field was fluctuating violently enough that the protection systems on the Hydro 735 kilovolt transmission network triggered automatically. 5 transmission lines from James Bay tripped. 9,450 megawatts of generation capacity disappeared in an instant. The system, carrying a load of 21,350 megawatts, could not absorb that sudden loss. It collapsed completely. Province-wide within 90 seconds. The entire hydro grid gone. 6 million people in the province of Quebec sat in darkness for 9 hours. The temperature outside was cold enough to be dangerous. There was no light, no heat, no warning, and no recovery for the better part of a day. The system-wide loss reached 19,400 megawatts. The material damage alone cost $5 million. The total damage reached $2 million in 1989 currency, and the event was classified afterward as a 1 in 50-year geomagnetic occurrence. The modern grid, engineers determined, could theoretically withstand a 1 in 100-year storm. The May 2024 storm had a return period of 5 years. The question of what a true 1 in 100-year event would do to the current American grid is not a question anyone in the power industry is willing to answer publicly. It is, however, a question that NASA and the University of Colorado answered in peer-reviewed research, estimating that each decade carries a 12% probability of a catastrophic solar storm capable of leaving 130 million Americans without power for more than a year. Think about that number in the way that a person standing in Montreal at 2:45 in the morning on March 13, 1989, would have understood it if they had had access to those projections. 130 million people, not for 9 hours, for more than a year. The city of New York alone holds more than 8 million people in its 5 boroughs. Add Chicago, Boston, Philadelphia, Detroit, Pittsburgh, Baltimore, Washington, Minneapolis, and every smaller city and town in the northeastern corridor of the industrial Midwest, the Upper Plains states, the Mid-Atlantic seaboard, and you begin to approach the scale that the research is describing. These are not abstract populations. These are people who wake up every morning with the assumption that electricity will arrive when they touch a switch. These are people whose hospitals run on power, whose water treatment plants run on power, whose fuel pumping systems, communication networks, traffic infrastructure, heating systems, and food refrigeration chains all run on power. A prolonged grid failure of the scale the research describes would not be an inconvenience. It would be a cascading infrastructure collapse the likes of which the continental United States has never experienced. The technical mechanism by which a G4 or G5 geomagnetic storm accomplishes this is not mysterious. It is documented, measurable, and already observed. When a fast coronal mass ejection moving at velocities between 750 and 1,500 kilometers per second arrives at Earth and compresses the magnetosphere while delivering a southward-oriented interplanetary magnetic field, it triggers a reconnection event on the night side of the planet. That reconnection drives an intensified ring current in the near-Earth space environment, which in turn induces variations in the magnetic field at the surface of the Earth. Those magnetic variations measured in nanoteslas per minute drive geomagnetically induced currents through the ground itself. The Earth's crust acts like a vast conductor, and where the crust is electrically resistive as it is across the Canadian Shield, across the crystalline basement rock of the upper Midwest, across the Piedmont Formation that runs east of the Appalachian Mountains, directly adjacent to the densest concentration of American cities on the eastern seaboard, those induced currents are strongest. The USGS Geoelectric Hazard Map published in 2020 confirmed exactly this. The highest geoelectric hazard in the contiguous United States sits in the northern Midwest and directly east of the Appalachians, in the area bordering Washington, D.C., New York, Baltimore, Philadelphia, and Boston. These induced ground currents enter the power grid through the neutral to ground connections of high-voltage transformers. They saturate transformer cores. They cause the transformers equipment that costs between $3 million and $10 million per unit and takes between 12 and 24 months to manufacture and deliver to overheat. And when a transformer overheats under geomagnetically induced current saturation, it does not simply trip offline and reset, it fails permanently. The regulatory landscape surrounding this vulnerability is what makes the situation genuinely alarming to anyone who reads the actual filings. NERC, the North American Electric Reliability Corporation, is the self-regulatory body responsible for setting reliability standards for the bulk power system. FERC, the Federal Energy Regulatory Commission, has the legal authority to order NERC to propose protection standards but cannot independently mandate them. NERC's current mandatory geomagnetic disturbance protection standard, TPL 0074, sets a benchmark geoelectric field of 8 volts per kilometer at 60 degrees geomagnetic latitude, scaling dramatically downward to approximately 2 volts per kilometer at Washington, D.C.'s geomagnetic latitude and to less than 1 volt per kilometer across the southern states. As of March 2026, a formal complaint filed before FERC asked the Commission to order NERC to assess and protect the grid against the international scientific standard 85 volts per kilometer. The difference between 2 volts per kilometer and 85 volts per kilometer is not a rounding error. It is a factor of more than 40. The current standard was not derived from North American storm data. The scientific community has said so publicly. The complaint says so on the public record, and yet the standard remains. The system is not adequately protected. The system is not inactive, it is accumulating vulnerability while the sun accumulates magnetic complexity, and the sun does not ask for regulatory permission. It does not wait for engineering studies to be completed or for FERC dockets to close. The May 2024 G5 storm arrived with a DST minimum of negative 412 nanoteslas, and some instruments recorded a spike to negative 518 nanoteslas. The AP index on May 11, 2024, reached 271, the second highest ever recorded in the modern instrumental record, surpassed only by November 13, 1960, when the index reached 280. The January 19, 2026 G4 storm arrived without extended warning. The active regions that produced the X8.3 flare, the strongest of 2026 at the time it occurred in the first days of February 2026, from Sunspot region R4366, demonstrated that this solar cycle's active regions are capable of rapid intensification, growing to dangerous complexity in a matter of days. And what solar orbiter is now tracking as it rotates toward the Earth-facing disk has not yet been assigned a NOAA active region number because it has not yet fully rotated into view. It is approaching helioseismic holography, the technique by which sound wave travel times through the sun's interior reveal magnetic concentrations. On the hidden surface is already detecting the signature. Perseverance on Mars has already imaged it. Solar Orbiter has already photographed it. 3 platforms, 3 confirmed detections, and not yet a single NOAA region number assigned because the feature is still beyond the limb. Consider the community of Plattsburgh, New York, a city of approximately 20,000 people on the western shore of Lake Champlain, less than 60 kilometers south of the Canadian border. Plattsburgh sits at high geomagnetic latitude. The crystalline basement rock of the Adirondack Formation to its west and south is among the most electrically resistive geology on the continental United States, precisely the geological environment in which geomagnetically induced currents are amplified and focused into the power grid. The people of Plattsburgh heat their homes. With electricity, their water treatment plant runs on electricity. Their hospital CVH Medical Center runs on electricity, with emergency backup generators capable of sustaining critical operations for perhaps 72 hours. They are connected to the New York grid, which is connected to the broader Northeastern Interconnect, which is the same network that in March 2024 was identified in NOAA's power grid vulnerability analysis as carrying elevated storm risk. A person in Plattsburgh on the morning after a major GMD event might ask the same question a person in Quebec City asked at 2:45 a.m. on March 13, 1989, what happened to the lights and when will they come back? In Quebec in 1989, the answer to the second question was 9 hours. In the scenario the NASA and University of Colorado research describes, the answer could be more than a year. The connected systems at work here extend beyond the simple chain of flare to CME to magnetospheric compression to grid failure. The Sun is not operating in isolation from the broader electromagnetic environment of the inner solar system, and neither is Earth's response to solar forcing as simple as a single number on the KP index. Scale: Solar Cycle 25 has proven more active than the initial consensus forecasts predicted. Scientists who study the Sun's deep magnetic dynamo, the engine beneath the visible surface that generates the 11-year cycle of activity, have noted that the current cycle's sunspot regions have displayed unusually complex beta-gamma-delta magnetic configurations, the classification reserved for active regions with the highest flare potential. The January 2026 research team that created the first system for predicting extended windows of superflare risk confirmed their model's accuracy precisely because Solar Orbiter detected far-side superflares including an X16.5 event on May 20, 2024 and X9.5 and X9.7 events on May 15, 2024 that their model had flagged as likely. The model does not predict the exact moment of eruption that remains beyond current science. What it does for the first time is identify windows of elevated risk and the specific regions most likely to produce extreme events, and the windows it is identifying as we move through May and into June 2026 are not windows of calm. There is a second connected system that carries less attention but no less consequence. The ionosphere, the upper atmospheric layer that begins approximately 60 kilometers above the surface and extends to 1,000 kilometers, is directly disrupted by the same solar radiation and particle fluxes that drive geomagnetic storms. During a major geomagnetic event, the ionosphere expands, its electron density becomes irregular, and the GPS signals that modern logistics, aviation, agriculture, and emergency response depend on degrade or fail entirely. The G5 storm of May 2024 triggered level are 3 radio blackouts across the daylight hemisphere. Navigation signals were disrupted. Satellite operators reported elevated radiation levels and temporary communications interruptions. High-frequency radio, the fallback communication system for aviation and maritime operations in the absence of satellite connectivity, failed across broad swaths of frequency bands. These are not secondary inconveniences. In the first hours after a major grid event, when utilities are attempting to assess damage, coordinate switching operations, and restore priority loads, the same storm that knocked out the grid will also have degraded the communications infrastructure the response depends on. The system does not fail in one place. It fails everywhere at once. What the data on this May 25, 2026 therefore presents is not a hypothetical risk profile. It is an active, real-time tracking situation in which a spacecraft not visible from Earth is watching sunspot magnetic configurations rotate toward the planet, in which NOAA has already officially stated that its solar activity forecast could change based on what Solar Orbiter sees, in which the Earth's power grid carries documented structural vulnerabilities in precisely the geographic areas of highest geomagnetic risk, in which the current solar cycle has already produced a G4 storm in January 2026 and a G5 storm in May 2024, and in which the planetary record confirms without ambiguity that what is being described has already happened. Not in computer models and not in risk assessments, but on a real grid, to real people, on a real night in 1989 when the lights went out across an entire province in 90 seconds. Scientists choose their language carefully here. NOAA does not say we expect a major storm. It says the forecast could change. ESA does not say Solar Orbiter has found a catastrophic region. It says the spacecraft is providing far-side imagery that is relevant to the forecast. These carefully chosen words are not evasions. They are the honest expression of what science can and cannot say at the boundary of predictability. Solar physicists can characterize the magnetic complexity of an active region. They can estimate the probability of a major flare. They can model the trajectory and speed of a coronal mass ejection after it erupts. What they cannot do, what no instrument on Earth or in space can yet accomplish, is tell you exactly when, exactly what magnitude, exactly which direction the interplanetary magnetic field will be oriented when the CME arrives. Those final degrees of southward orientation, the B's component of the interplanetary magnetic field tilting south at precisely the wrong moment, are what converts a moderate storm into a grid-threatening one. And that tilt is not measurable until the CME is approximately 30 minutes from Earth, arriving at the L1 Lagrange point where NASA's IMAP spacecraft, which entered operational orbit around L1 in early 2026, is now positioned 30 minutes. That is the window between detection and impact. That is not hours. That is not days. That is the duration of a short meeting. Minutes are not hours, and in this context, that difference is everything. The preparedness landscape as of May 2026 is not one of confident protection. A formal complaint before FERC, filed in March 2026, explicitly argues that the existing NERC reliability standard is scientifically inadequate, set to a benchmark that is not derived from North American storm data, scaled down so dramatically across geomagnetic latitude that Washington, D.C., is effectively protected against only 2 volts per kilometer of geoelectric field, while the international scientific community has identified 85 volts per kilometer as the appropriate reference level for serious hazard assessment. The complaint tasks FERC to require NERC to update the standard. That process, if initiated, will take months. The active regions rotating into Earth's view from behind the solar limb will take days. The people who will not have had this conversation in advance are not irresponsible. They are simply living in the present, as all people do. They are in Chicago, where the population of the greater metropolitan area exceeds 9 million. They are in Cleveland, in Milwaukee, in Detroit, in Pittsburgh, in New Haven, in Providence, in every city and suburb along the eastern seaboard where the geology is most resistive, the transformer infrastructure is most exposed, and the population most densely concentrated. They wake up each morning and turn on the lights. They plug in their phones. They warm their food. They do not think about the transformer sitting in a fenced utility compound 3 kilometers away, and they do not think about the invisible current flowing through the crystalline basement rock beneath their feet that a southward-oriented interplanetary magnetic field, in exactly the right quantity, at exactly the right moment, could amplify into a permanent failure of that transformer. They do not think about this because they have not been given a reason to think about it. This is that reason. This is not a hypothesis. This is documented in the geological record and in the engineering record and in the regulatory record and in the peer-reviewed scientific literature. The March 13, 1989 blackout. Is the archetypal event the phrase used by Dr. David Bottler, head of the Space Weather Group at Natural Resources Canada, and it is exact. Archetypal, meaning it is the defining instance of a class of events that includes the Carrington event of September 1859, the Great Railroad Storm of May 1921, and the Halloween storms of October 2003 that caused widespread grid interference across North America and a blackout in South Africa. These events are not the edges of the distribution. They are the recurring pattern of a system that has been doing this for 4.5 billion years and that, as Solar Cycle 25 has already demonstrated, has no intention of decelerating. The instruments are in place. Solar Orbiter is watching. NOAA is forecasting. IMAP is waiting at L1. And somewhere on the far side of the Sun, rotating toward the eastern limb of the solar disk at the rate of approximately 13 degrees per day, the precise rotational speed of an active region carried by the Sun's differential rotation, a magnetically complex structure is completing its journey into view, whether it erupts, whether the eruption produces an X-class flare, whether that flare launches a full halo coronal mass ejection directly toward Earth, whether the CME travels at the speed required to compress the magnetosphere efficiently, whether the interplanetary magnetic field arrives southward. All of these are open questions. The science can assign probabilities to each. It cannot collapse them to certainty. And that uncertainty is not a reason for complacency. It is the precise condition under which the March 1989 blackout occurred, not because no one knew a storm was possible, but because no one knew in the final hour exactly what was coming. The Sun has been doing this since before the first human eye ever turned toward the sky. Every active region that rotated into view across 4.5 billion years of solar history did so without an audience capable of measuring it, recording it, or protecting itself from it. We are the first civilization in Earth's history with the instruments to watch it happen in real time, and the first civilization in Earth's history with an infrastructure complex enough and fragile enough to be collapsed by it in 90 seconds. That gap between the watching and the protecting is not a technical failure. It is a decision. And on May 25, 2026, while Solar Orbiter transmits its far-side magnetic imagery back to Earth and NOAA updates its 27-day space weather forecast and the IMAP spacecraft waits at the first Lagrange point 30 minutes ahead of whatever is coming, that decision has not yet been made. The Sun has not finished rotating.